Welcome to logs. No, not those logs. Logarithms.
Confused by all these math terms? Don't worry, we'll teach you how. Let's get started.
The parent function that we're going to be talking about are logarithms, or also known as logs. Now, logs have a very similar relationship to exponential functions because they are its inverse. And what I mean by that is if we were to write the exponential parent function algebraically, it would look like this. B to the x equals y, which we're very familiar with, or we should be very familiar with. And if we were to write the parent function for logarithms, it would be looking like this. Log b to the y equals x. And you can see similar variables in both of them. So we have b right here, which is our basis for both of them. And then you have your exponent, which is raised to that power, which gives you your answer in logarithms. And then this base right here in your logarithm is your answer to an exponential function. So let's write that out in numbers to make it a little bit less confusing. So if we were to take our traditional 5 squared equals 25, that's our exponential function. But if we were to transform that into a logarithmic function, we would use log 5 since, hang on just a sec, I messed it. Alright, it's going to go down. Log 5 since these are both our bases. And if you have your 25, which is the base right here like we talked about, equals 2, since that's what our x is raised to, and in a logarithmic function, our answer is x.
Taking a look at the zeros of this logarithmic function, you can see that the uphill line, which is our parent function, touches the x-axis one time at the point 1, 0. So that's going to be our 0 for a logarithmic parent function, 1, 0. Moving on to the y-intercept. The y-intercept is when the line of the graph touches a point at y. Looking at our parent function, this is obviously not the case since our y-axis represents an asymptote to our logarithmic function, so there is no y-intercept to a parent logarithmic function. As for one-to-one correspondence, which basically all you do is do a horizontal and vertical line test. If you were to take that logarithm that's sloping down, since these are two different lines, if you take one of those lines, you can do the vertical and horizontal line test to find that logarithmic functions have one-to-one correspondence.
The logarithmic function f of x is equal to the log of x has continuity because when you draw the graph you do not pick up your pencil. Also, when the function has an outcome from 0 to 1 as a fraction, it is flipped. Just like this.
Now for domain and range. So we know the definition of range is all the possible values of y. So range is all the y values, and domain is all the possible x values. So on the graph you can see that the x value right here is never going to hit 0 because this y-axis serves as an asymptote. So even if this goes down all the way to infinity, it's never going to touch that y-axis. So the domain will never be 0. So when you write this, it's going to turn out that domain is going to be, you're going to draw parentheses, and it's going to be 0 to infinity. Because it's, when you're talking about the x-axis here, all the x values can be anything greater than 0, and it can go on to infinity. So when you write this, it's important to draw parentheses because the parentheses indicate that you're only talking about the values, the values inside of the ones listed. So you're not going to actually include the number infinity or the number 0. However, it's all the numbers in between that. So when you talk about range, the range is going to be all the values of y. So as you can see, as this increases, it's going to go on forever and ever and ever, and it's eventually going to go on to infinity. And for negative y, it's going to go on to infinity as well. So the range is simple. It's negative infinity to positive infinity. And again, we're using parentheses because infinity is not actually a number. So your domain is 0 to infinity, and your range is negative infinity to positive infinity. Okay, now for a line of symmetry. A line of symmetry is when the function is directly reflected across either the x or the y axis. You can also rotate it around the origin 180 degrees and it will end up in the same spot as before. So let's test to see if logarithmic functions have line of symmetry. So first let's test across the x-axis. So we're going to flip it up and down, and you can see that this continues to go on forever, so it's not going to be a mirror image as it was before. So it's not reflected across the x-axis. Now let's try the y-axis. And you can see it would end up over here. And that's, of course, completely opposite. So we know that it's not y-axis. So the last thing left would be to rotate it 180 degrees around the origin. So in order to do that, it would end up looking like this, which in order to be a line of symmetry around the origin, you have to end up in the exact same spot when you rotate it 180 degrees, and obviously this is not. So line of symmetry is non-existent for logs, and this can also be explained by the fact that logarithm functions are neither even nor odd, so that also explains why there is no line of symmetry.
Now we're going to talk about end behavior, and end behavior is what a graph does at extreme points. So we're going to talk about the x and y values. So as x approaches infinity, so as x is going this way, y also approaches infinity because as it goes this way, it's also going up too. And as x approaches 0 right here, y is also approaching negative infinity, as you can see, but it never exactly touches 0 at y. And to write this out mathematically correct, we're going to say as x approaches 0, y approaches negative infinity, and as x approaches positive infinity, y approaches positive infinity as well.
Is the log function even or odd? Well, because there is no line of symmetry between it, it cannot be divided into any equal part on each line. There's no line of symmetry. It cannot be odd or even. For example, if the log base 5 of 25 is 2, but the log base 5 of negative 25 comes up as an error and it cannot be graphed because both outputs are not equal, they're not even, and because they're not opposites, they are also not odd.
That's right, time for a game! Here's how the game works. I will have a graph like this one you see, and you will have to answer out loud. I will explain the right answer after time to let you think, sort of like how Dora the Explorer does it. Let's try it on this graph, which shows all translations. I could say, is the blue line a vertical shift or horizontal shift? And you would say vertical, because the parent function is in black and the blue one went up from the parent. That was your freebie, so let's get serious. This one's also your freebie since this was the blue one in the graph before. Tell me, is this a horizontal or a vertical shift? That's right, It's a horizontal shift because the parent function starts out going through 1, 0, and now it's going through -2, 0. This graph shows all reflections for logarithms. Tell me, is this a reflection over the x-axis or the y-axis? Good! It's a reflection over the x-axis, which is the horizontal line right there. And if you were to fold your paper, you would get this picture on the graph right here. Tell me this, would this be a reflection over the x-axis or the y-axis? You got it, it's a reflection over the y-axis, because if you were to fold it along the vertical line, the y-axis, you would get the picture shown in front of you. Is this a vertical shrink or a vertical stretch? Good, it's a vertical shrink because it has been compressed vertically by 1/2. Now tell me, is this one a vertical shrink or a vertical stretch? Well, the parent function in the background kind of gives it away. It's a vertical stretch because you can see that even though it still goes through the same point at 1, 0 as the parent function, it's stretched vertically. Looking at this graph, is it a horizontal shrink or a horizontal stretch? That's right, it's a horizontal stretch because if you look at the equation above, it says log 5, but really you're multiplying by the reciprocal, giving you a smaller number. Now is this graph a horizontal shrink or stretch? That's right, it's a horizontal shrink because, talking about reciprocals again in the equation, this one is 3, which is 1/3, which is a little bit bigger, so it makes the graph a little bit smaller. Let's review the domain and range changes in our transformed graphs. When we talk about vertical and horizontal shrink and stretch, the domain and range aren't really affected since it's scale factored in the same spot and the log goes in the same direction. However, when we talk about a reflection in the x and y values are changed to their opposites, so the domain and range can change the same way. As for vertical and horizontal shifts, vertical shifts won't change domain and range-wise because of the y-asymptote, but horizontal shifts can change the range and domain since you saw in the previous picture that the function went through the y-axis and that changed the asymptote rule there. In conclusion, logarithms are all around us, and the items discussed and taught in this podcast, such as in behavior, continuity, transformations, and so on, will help you to acknowledge not only logs, but math in the world we live in. Thank you!